Reality is complex. The complexity of reality makes it very difficult to fully understand. But if we simplify reality somewhat, we can get a much clearer picture of the general scope of how reality works. In science, we take a sample of reality, measure it, and then simplify it into a model. Of course, the trade-off for simplifying reality is that our simplified model will lack the complexity of the real world. On the other hand, not all models are created equal, and some models are a good fit to the data of reality. Other models are a poor fit and tell us less than we would like to know. When our model generally looks like reality, it is a good fit, and what we learn from our model can tell us a great deal about the real world. Descriptive statistics create a model of the population using what we learned from our sample. Every measurement in our sample tells us something about the population, i.e., reality. One such descriptive statistic that works well as a model for reality is the mean. What we learn from our sample mean, m, or x bar, can tell us a lot about the population mean that we have not actually measured. The population mean is called mu. We want to know how well does our model, m, represent mu. So let me explain what I mean when I tell you that the mean is a model. The mean of the sample, m, is always the best estimate for the mean of the population, mu, from which the sample was drawn. The mean of the sample becomes our model for the population. So say that you measure and find out that the average height of your baseball team is 5'10". With only that information, what do you estimate is the average height of all baseball players? Your best estimate of the population mean is your sample mean, 5'10". The mean also works as a predictor. The population mean, mu, is always the best prediction for any sample, m, drawn from that population. What is true of the population should be true of any sample drawn from that population. So if you were told that the average height of all baseball players is 5'10", what would you predict will be the average height for your baseball team, assuming you have not measured them yet? If you know that your sample, your baseball team, is drawn from a population with a mean of 5'10", then your best prediction of the average height for your baseball team is 5'10". And this prediction also works from the sample to individuals in that sample. The sample mean, m, is the best predictor for any particular subject, x, in that sample. You know that the average height for your team is 5'10". You randomly select one baseball player from the roster. What do you predict will be his height? Knowing nothing else except that the rest of the team has an average height of 5'10", so most players on the team are close to 5'10", your best prediction of his height would be 5'10". If you knew additional information about the player, you might add or subtract inches from your guess based upon that additional knowledge. If you knew that he was a pitcher or a shortstop, players who tend to be a little taller, you might guess a little higher. If you knew that he was a catcher, you might guess a little lower. But given no other information than the average height of the team, your best guess would always be the sample mean. So keep this in mind for the future. The mean is a model. And if we know something more, we can use the mean as a starting point for adjusting our predictions of what we expect. So for instance, if I told you that a sample was drawn from a population with a mean of 100, what would you expect the sample mean to be? 100. But if I told you that the sample mean was actually 150 and that sample had undergone a treatment, such as being given caffeine to drink, how might you explain why the sample mean is now 150 rather than the expected 100? Well, we might conclude that caffeine improves performance. And if we also knew that the population mean expected of caffeine-improved performance is 148, then the sample mean of 150 makes even more sense. The sample was drawn from a population with a mean of 100, then given a treatment, and after treatment, the sample mean was 150. That 150 sample mean is more representative of the population defined by caffeine-improved performance than it is of the original untreated individuals. We can use our sample means as a model to better understand reality.